Hi everybody, and welcome to our first video on trigonometric integrals. These are going to be integrals which, maybe unsurprisingly, have trigonometric functions in them. For example, say I wanted to find an antiderivative for the cube of the cosine function. Now I could use integration by parts here, but there's going to be a somewhat simpler way by using a very common trigonometric identity. Let's see. Say I draw a unit circle. What's a unit circle? Right. It's going to be a circle whose center is at the origin and whose radius is 1. Now, I'm going to draw a ray from the origin out through the circle, and it's going to intersect at some point. And when it intersects, it's going to give me some angle, and okay, maybe we'll call this angle, I don't know, theta. Right? Now, I want to know what are the coordinates of that point. And it turns out the coordinates of this point are cosine of theta, comma, sine of theta. Now this is really nice because if we turn around and draw a right triangle now, right, we just draw a perpendicular here, the height of this triangle, well, it's just the y coordinate, sine of theta. And the base of this triangle, down here, is just the x-coordinate, cosine of theta. The hypotenuse of this triangle, well, it's a circle of radius 1. The hypotenuse has length 1. So now we can use the Pythagorean theorem to write down the following identity. If we take the square of one leg, sine, and we add to it the square of the other leg, so that would be the square of the cosine, we get the square of the hypotenuse. Well, the hypotenuse is 1, 1 squared is 1. And so we get what is sometimes called the Pythagorean identity. Sine squared plus cosine squared is equal to 1. Now, there's a very quick way to rearrange this. We can rewrite cosine squared as 1 minus sine squared. If we do that, we're now going to have a way of breaking this integral up and making it a little bit easier. Let's see. So, I'm going to first rewrite cosine cubed as cosine of x times cosine squared. Why? Well, I want to use this formula, right? It's got a cosine squared. That didn't. Okay, fine. I break it up. Now I use the formula. I rewrite cosine squared as 1 minus sine squared. Now if I do that, I can now distribute cosine times, well, let's put some parentheses here just for emphasis. I can rewrite my antiderivative as the antiderivative of cosine times 1. And then another antiderivative, it gets a minus sign, of cosine times the square of sine. Okay, what's the advantage of this? Well, first, here's an antiderivative we just know. All right, this guy down here, that's just sine of x. Okay, plus a constant of integration, but we'll add that back on all at the end. Now what happens over here? Well, this looks rather complicated, but notice I have a sine and I have its derivative, cosine, which means I can do a U-Substitution. All right, I'll call U sine of x so that this becomes u squared. And then what would my du be? My du, if u is equal to sine of x, my du will be cosine of x dx. Hey, I've got a cosine of x dx. That becomes my du. Sweet. So all I'm really doing is integrating u squared. That's totally easy. That's a third u cubed. Okay, wait, but u is sine of x, so what do I get? I get minus a third u cubed, but u is sine cubed. Okay, so of course, what do we need at the end? Our constant of integration. So by using this Pythagorean identity, we were able to turn this fairly complicated looking trigonometric integral into two different integrals, one of which is, well, just a formula we know, and the other is just one we can use a basic substitution on. This is even easier than using integration by parts on such a problem.